Hi everyone, and welcome to our Priority Education YouTube channel. Today we're going to be looking at some A-level chemistry revision. So big shout out to all my year 13 students who I know are working super hard at the moment. Hopefully we're going to do a question today that will help you out a little bit. The question that we're going to be doing is on the acid-base topic. We're going to have a go at calculating a Ka value. It's a common question that comes up, but well worth getting your teeth stuck into, as it's often worth a lot of marks in the exam. All right, let's get going. Okay, so this question is going to look at calculating a value for Ka. Remember, Ka is a constant, it's the acid dissociation constant. It allows us to link the products to the reactants in an acid-base equilibrium. So let's have a look at this one. It's from an AQA paper, but also very relevant to the OCR spec as well. So a solution that contains 605 milligrams of NaHSO4, that's sodium hydrogen sulfate, in 100 centimeters cubed of solution has a pH of 1.72. Calculate the value of Ka for the hydrogen sulfate ion, that's HSO4 minus, that is behaving as a weak acid. Give your answer to 3 significant figures, and we're going to state the units of Ka as well. And as you can see, 6 whole marks for this one, so well worth being able to get your teeth stuck into this one. So the first thing that I would do is I would get my lovely highlighter out and highlight some of the key things. So we've got 605 milligrams, alarm bells instantly going because we measure in grams in chemistry. We've got sodium hydrogen sulfate, and that 605 milligrams is in 100 centimeters cubed of solution. Again, we're going to want to convert that into decimeters cubed for our chemistry value. The pH has got a 1.72 value, and we've been given the information that our HSO4 minus ion is behaving like a weak acid. We're also going to want to take note of this when we're quoting our final answer. That is to 3 significant figures. I would hold as many decimal places as possible in your calculator right till the end, and then we're going to put it in as a 3 significant figure value. And don't forget, often this is worth a whole mark on its own, that once we've got our value, we're then also going to make sure we state our units of Ka. Now, the first thing that I would do is just get my head a little bit around what's going on here. So we've been told that, yes, we've got sodium hydrogen sulfate, but it's the hydrogen sulfate ion that we're interested in, and it's going to be behaving like a weak acid. So what's going to be going on there is our HSO4 minus ion is going to be in equilibrium, whereby it's going to act like an acid. So it's going to become a Bronsted-Lowry proton donor, and then we're going to be left with our sulfate ion there like that. The next thing is I'm going to remind myself of how we're going to calculate Ka. So if we're calculating Ka, we're going to want an expression for that. Now the general expression is it's the concentration of the products. So a general way of writing this is the concentration of the products over the concentration of the acid. And remember, those square brackets mean concentration. Now, if I apply that to this question, it becomes Ka is equal to our H plus concentration times our SO4 minus concentration over our acid concentration, which is HSO4. And remember, this is something that we do when we're looking at weak acids. Now, I can see that I've got the pH, so that's going to allow me to instantly be able to work out the concentration of hydrogen ions in my equilibrium. Haven't got anything to work out my sulfate ion, so what I can instantly do is just change this expression to the version where, because they're going to be in the same concentrations, I can do the hydrogen ion concentration squared over the hydrogen sulfate ion concentration. So that final expression is what I'm going to be working with. H plus ion squared over our hydrogen sulfate ion concentrations. Okay, now the easy bit is to use that pH to work out the hydrogen ion concentration. So in order to do that, the hydrogen ion concentration is going to be equal to 10 to the minus 1.72. Remember, hydrogen ion concentration is 10 to the minus pH, and our pH there was 1.72. And if you plug that into your calculator, you should get a value of 0.0191 moles per dm cubed, because it's a concentration. Okay, so I've now managed to work out this, and obviously I would square it on the top of that fraction there. Now what I'm going to do is I'm going to try and work out my hydrogen sulfate ion concentration. Now what we've been given is we've been given the concentration of our sodium hydrogen sulfate at the start of the equilibrium. So it's not the equilibrium amount, it's what was put in at the initial start of the investigation. So what I'm going to consider then is, well, NaHSO4 moles is going to be equal to the moles of HSO4 minus, which is the one we want for our Ka expression. So I can work that out, and then I've got a way of trying to get to the concentration of our hydrogen sulfate ion. Now it's worth pointing out here that this is just at the initial. We're going to have to take into consideration in a moment what that value is going to be when the solution's reached equilibrium. Okay, so initially then what I'm going to do is, well, we've been given the grams, we've been given the milligrams, so let's just convert those grams into the milligrams into grams. So I'm going to divide that by 1,000 to get my answer in grams, and then I'm going to be doing my mass in grams over my MR in order to get the moles of my sodium hydrogen sulfate, which will give us in turn the same moles of hydrogen sulfate ion. So if I plug that in, I'm going to get 0.605 grams, and then I'm going to do my whole moles is equal to mass in grams, which we've now got, over the MR of sodium hydrogen sulfate. So that becomes 0.605 grams over, if you add up the AR of sodium, hydrogen, sulfur and 4 oxygens, you get 120.1. Okay, and ultimately when all of that's plugged into your calculator, you are going to get, I believe, 5.04 times 10 to the minus 3 moles. That's a 3, by the way. There we go. So now we've got our moles. We've got our moles of our hydrogen sulfate ion. But in order to be able to plug it into that Ka expression, we've now got to get it into a concentration. So what we would do is we're going to rearrange the concentration is moles over volume 1. And so we don't need to rearrange it. Actually, we're just going to divide the moles by the volume. So if we get the moles, 0.4 times 10 to the minus 3 moles. And if we just scroll back up, you can see that it was in a solution of 100 centimetres cubed. So again, I'm going to have to convert that to decimeters cubed by dividing by 1,000. And so I would divide my moles by 0.1 decimeter cubed. And if you get that, then what you will have is 0.0504 moles per dm cubed as our concentration of hydrogen sulfate ions. Now, once we've got all of that, we can just plug it into the equation. Running out of space here, so let's do it over here. So I'm going to put for my hydrogen ions, we got it as there we go, 0.0191. Don't forget to square it, and then in order to work out our hydrogen sulfate ions, we've got to remember that we worked out what it was initially, okay? So the value that we got was what it was initially. At equilibrium, we've got to adjust that slightly. So how we would adjust that, if we think sensibly, well, if we've got if we've got a concentration 0.0191 of our hydrogen ions, well then we need to subtract that from the concentration of our acid. So we can do 0.0504 take away 0.0191, and that would give us what we have on the bottom of that equation. Now plug that all into your calculator and you should get a Ka value that is equal to 1.17 times 10 to the minus 2. And our final thing is to calculate the units. So how we're going to work out the units, I'm going to add another page now, as lots of work in for this one, well, if we think about our Ka expression, well, we had our hydrogen ion concentration squared over our concentration of our hydrogen sulfate ion. So what we're going to do, well, our units would be moles per dm cubed, but it's squared, so we're timesing those together on the top. I always write it out in full so that I can just cancel down to make sure that I've got the correct unit there. So it's over 1 moles per decimetre cubed. So if I cancel that out, then what I'm left with is moles per decimetre cubed on the top of the equation, and that would therefore be my unit. So the final answer would be Ka is equal to 1.17 times 10 to the minus 2 moles per dm cubed. Now that is a whopping 6 marks, so as I said, well worth getting your head around it, and a brilliant chemistry question because it enables you to show off all your valuable knowledge that you've been learning over the past 2 years. All right, well, thank you very much. If there are any other questions regarding this one, or if there's any other topics that you want me to look at next, then just comment in the comments below, and please subscribe and share with any of your chemistry friends who might be revising at this point. All right, bye.